Welcome to solverfy.
Hello, we are going to balance some equations today. Now I'm going to be a little bit lazy and not write the states down, whether they're solid, liquid, gas, and so forth, because that actually doesn't matter when you're balancing, right? Just to keep things as simple as possible, I'm going to write it like this. All right, now sometimes with these big equations, when we have you balance them, it can be a little hard to keep track of how many you have of each one. And so I recommend doing a kind of a way to keep track of them as you go until these become really comfortable and you don't need to do this anymore. Some people always do this. Some people just do it in the beginning. But we're just going to count up how many of each one we have. So calcium on the left-hand side, we've got 3. Phosphorus, we've got 2. Hydrogen, we've got 2. And oxygen, we've got 1. Next one, we've got calcium. We've got 1 of those. Phosphorus, 1. Hydrogen, now, there's 2 hydroxides, which means there's 2 separate OH groups. So there's 2 hydrogens coming from this part right here. And then there's another 3 hydrogens right there. So that's a total of 5. And then with the oxygen, it's the same logic. We have 2 copies of the OH groups, so that means 2 oxygens. And the whole point is to just make it so the numbers on both sides equal. We want the same number of each atom. With this one, I didn't see anything that was going to heavily trip us up, which means we can just kind of start wherever we want. We might as well start with the calcium. We've got 3 and 1. Okay. Now, when you're balancing, the only thing you can change is the number out front. Right? We call those coefficients. Okay, those are the only things you can change when you're balancing. For example, I could not put like a 3 right there after the calcium, like Ca3, because that changes what the compound is. But you can put numbers out front. That changes how many of that compound you've got, but it's still the same exact compound. There's just like 3 copies of it. Okay, so that changes the calcium to 3, but it also impacts other things as well, because if we have 3 compounds and each one has 2 hydroxides, 3 times 2, we have a total of 6 OH groups, which means 6 oxygens and 6 hydrogens plus the 3 that are over here. So that's a total of 9 hydrogens. All right. Next step. Let's look at the phosphorus. We've got 2 and we've got 1. So let's put a 2 in front of the pH3. That'll get our phosphorus up to 2. It will also impact our hydrogens, because now we've still got the 6 hydrogens from the calcium hydroxide, plus another 2 times 3, which is 6, for a grand total of 12. Right. Last thing to do is to balance our hydrogens and oxygens. And if you actually balance one of them in this case, it balances the other. So let's look at the hydrogens. We've got 2, and then we've got 12. Easiest way to deal with that is going to be to put a 6 in front of the hydrogen. 6 times 2 is 12, and then 6 times just the 1 oxygen gets that up to 6. So we have actually knocked out both hydrogen and oxygen in that one. So there's your balanced equation. All right, let's write out the next one. We are doing aluminum hydroxide plus sulfuric acid to make aluminum sulfate and water. Go ahead and scroll down. Just like we did on the last one, we're going to take stock of how much we have. Okay. Now, there's some tricks that you can do to make your life a little bit easier on this problem. Right? And one of them is to keep an eye out for polyatomic ions that show up on both sides. For example, the sulfate, SO4, which is sulfate, shows up on the left, and then it shows up on the right, and it's still intact. It's still SO4. Right? That means instead of counting those sulfurs and oxygens separately, we can just track them as SO4. Right? So let me show you what I mean. We're going to do aluminums. We're going to do oxygen and hydrogen, and then we're going to do sulfate, like that. Okay. The hydroxide is also a polyatomic ion, but it doesn't show up the same. It shows up in the form of water later, which isn't the same format. So we're not going to track hydroxide that way. We're just going to do the sulfate. This is going to make your life a lot easier, especially when it comes to tracking how many oxygens you have. Okay, and we'll see that in future examples as well, where we do that. So we're going to do aluminum, oxygen, hydrogen, and sulfate. I try to keep them in the same order on both sides, like aluminum, oxygen, hydrogen, sulfate, so they match. Okay, let's fill them in. On the left, we have 1 aluminum. We have 3 times 1, which is 3 oxygens. 3 hydrogens plus 2 more, so that's 5. And then 1 sulfate. Okay, on the right-hand side, we've got 2 aluminums. Okay, ignore the oxygens and the sulfate, go over to the water. We've got 1 oxygen, 2 hydrogens, and 3 sulfates. Okay, all right, we're going to work through the same process we did in the last one. Just let me clean it up a little bit. There we go. We can start with whatever we want to in this case. Aluminum, we've got 1, and then we've got 2. So let's put a 2 in front of the aluminum here. Changes that to 2. Okay. And then we need to check how many oxygens and hydrogens we have because that changed those values. So now there's 2 times 3, which is 6. So now there's 6 oxygens. Remember, we're ignoring the sulfate. We're pretending like the oxygen and sulfate only belongs to sulfate. We have 6 hydrogens there plus the other 2. So that makes that, what, 7? Alrighty, and now our aluminums are balanced. Next, we can go ahead and take a look at, who do we want to look at? Honestly, we can do any of them. Oxygen, sure, why not? Oxygen, there's 6 on the left and then 1 on the right. So we could put a 6 in front of the water. That would change that to 6. It would also impact the hydrogens on that side. Now we have 6 times 2 per water, so that's a total of 12 hydrogen. Okay, so now the oxygens are taken care of. We're just kind of moving down the list. Now let's look at hydrogen. Actually, let's do sulfate, because oftentimes when you see an atom showing up, and when you see a single element showing up in more than one place, like we have hydrogens here and here, when they show up more than once on one side of the equation, leaving them till last will commonly make your life easier. So let's do the sulfate, and then we'll take care of the hydrogen last. A lot of the times, if you take care of everything else first, like the hydrogen will take care of itself. Like it'll be fixed. Okay, so we have 3 sulfates, and then we only have 1 sulfate. So we need to have 3 there, I think. Yes. Because that'll change the sulfate to 3, and that impacts the hydrogens. So we've got 6 hydrogens from right there, and then we've got another 2 times 3. We have another 6 there. So there's 6 and there's 6 for a total of 12, which has in fact fixed the hydrogen as well. Perfect. So there's that one done. All right. I might go a little bit quicker on these other ones as we're getting them down. We've got silver nitrate plus sodium carbonate goes to silver carbonate and sodium nitrate. We're going to track just like we did before. We've got silver. Now we've got nitrate, that's a polyatomic, and it shows up intact on both sides. It doesn't get broken apart, it stays as a chunk. So we can just track it like that. Then we've got sodiums on both sides. And then another polyatomic, CO3, which is carbonate. It is also on both sides intact, it didn't get broken up. So we're going to treat it as a chunk. This is going to make tracking the oxygens in this problem much, much easier. Because the oxygens get a little bit out of hand since it's in every single molecule. Okay, on this side, we'll do the same thing. And now we're going to start filling in. So on the left, we've got 1 silver, 1 nitrate, 2 sodiums, 1 carbonate. Right-hand side, we have 2 silvers, 1 nitrate, 1 sodium, 1 carbonate. Might as well just start at the top and work our way down. First up, we've got 1 silver and then 2 silvers. So let's put a 2 in front of there. That's going to change that to 2. It also changes us to 2 nitrates. So then we can look at nitrate and fix it. We've got 2 and then 1. So let's put a 2 on this side. Changes that to 2 and that to 2. And look at that, we're done. All right. I will tell you, if you count the oxygens individually, this looks much, much nastier than if you group them like that. Okay, we've got one more, and it is an absolute doozy. It is a combustion reaction, a nasty form of one. Let me get this written out. CO2, water, and N2. Okay, this one doesn't have any polyatomics to make our lives easy, so we have to track everything individually. H, N, and O, C, H, N, and O. All right, left-hand side, we've got 2 carbons. Hydrogens, but they wrote the equation in a little bit of an odd order. There's 5 and then another 2. There's a reason they wrote it like that. It's because of how everything's connected. But you don't need to worry about that. We've got 1 nitrogen and 2 oxygens. Right-hand side, we've got 1 carbon, 2 hydrogens, 2 nitrogens, and then oxygen shows up in 2 different compounds. We've got 2 there, and then another 1 for a total of 3. Let's clean that up, and we'll start balancing. Okay, I am going to tell you right now, we are going to leave oxygen until the very end. This is one of those situations where one element starts showing up in multiple compounds on a single side, where we have oxygen and then oxygen again on the same side. Completely ignore it, deal with everything else. The reality is there's more than one way to get the oxygens in this reaction to balance, but only one of those ways balances everything else as well. And if you try to start with oxygen, the odds of balancing it the correct way the first time is really low. You end up getting yourself into a rabbit hole, and I'm sure you've been there when you've been balancing and it just keeps going back and forth and your numbers keep getting bigger and bigger and you just don't know where it's going to stop. So we're going to skip the oxygen, deal with everything else first. All right, let's just start at the top and we'll do carbon. Actually, I take that back. I did notice when I did this, there is something to take note of. Nitrogen comes in pairs on the right-hand side. They have to be in pairs of N2. But on the left-hand side, you just get one at a time because it's in that C2H5NH2. The only way to get it so the nitrogens would balance would be for the left-hand side to be an even number. This happens every once in a while. So we're going to start by putting a 2 right here. So we're just going to balance nitrogen first. This is to make your life easier. I didn't do it first when I did it, and then I had to go back and redo it. So that changes the nitrogen to 2. It changes the carbon to 2 times 2 is 4. And then those 7 hydrogens also get multiplied by 2. So now it's 14. Okay. Now we can just kind of start from the top and work our way down. So carbon. We've got 4 carbon and then 1. So we're going to put a 4 in front of the CO2. That is going to impact the oxygen because now there's 4 times 2, which is 8, plus the other. So we've got 9 now. Okay. Next up, we can do the hydrogen. Okay. We've got 14 and then 2. So let's put a 7 in front of the water. That also impacts the oxygen. So we've got 8 here, and then we've got another 7. What is that, 15? We've got 15 nitrogen, or not nitrogen. Wrong one. 15 oxygen now. Okay, we've actually run into a similar issue we had with the nitrogen. Oxygen on the left only comes in pairs, 2 at a time. So no matter what, there's going to be an even number on that side. And yet on the right-hand side, we need 15. Okay. Now, when that happens, and you've already balanced everything else, this is a trick that tends to come up on combustion reactions, which this is, right? And it's almost always oxygen that causes it to happen. When you have an even number on the left or on one side and an odd number on the other, and it's not really easy to fix. The nitrogen situation was easy to fix. We could just put a 2 in front. Okay. But if we try to make the right-hand side even as it is right now, we don't know which one to change. And no matter what we change, it's going to mess up the balancing of everything else because we already did everything else. So what we're going to do, bear with me, this is going to feel weird. We're going to multiply the entire equation by 2. All right, bear with me. Some teachers show this 2 different ways. Some use a fraction and some do it this way, but they're both the same technique. So what I mean by multiply by 2, every coefficient is going to get multiplied by 2. So 2 times 2, that's now going to be 4, C2H5NH2. Ignore the O2 because that's what we haven't balanced yet. That's what we're trying to balance now, so you don't have to worry about it. 4 times 2 is 8 CO2s. 7 times 2 is 14 H2Os. And then 1 times 2 gives us 2 N2s. Now, this has not undone any of the work we've already done, which is important. Everything we've already balanced, the carbon, hydrogen, and nitrogen, is still balanced because what we did to everything. We multiplied everything by 2. So once again, the only issue is the oxygens. So let's try it again. Let's add up our oxygens. We've got 8 times 2, which is 16 oxygens, and then plus 14. Okay, so 16 plus 14 is 30. Okay. Well, we can get 30 oxygens by putting a 15 right there. Okay. And yes, that is on purpose. That the number we needed before ends up being the number there. Okay. Okay. Again, this comes up every once in a while, but often enough you want to be comfortable with it. And it happens when, usually with oxygen, and you've got an even number on one side and an odd number on the other, and it's not easy to fix it. It's not like obvious like it was with the nitrogen. All right, and there you go.